All right, let's talk about how point-to-point connections work. Of importance this time around will be the good old HDLC. The point-to-point protocol will be introduced. HDLC is the default on a Cisco router. That's why they care about it. And there is a difference between right-clicking on a thing and left-clicking on a thing. So I invite you to take some time out as a class and do the PPP persuasion activity. We'll pause the video and do that and come back. Okay, moving on. So if you took like the A+ exam 5 years ago, you might remember the difference between a serial interface and a parallel interface. Here we've got our service providers on one end between two LANs. We've got our serial interface at the top and our parallel interface at the bottom. And you can see how if you've got 8 bits to send across a wire, the parallel connection goes a lot faster than the serial connection, which was why you had your cool printers back in the day with the big fat Centronics connector on one end and a parallel port on the other, and that's how you'd send print jobs because they needed to go fast. So what we're showing here is that in the time it takes our serial connection to send a byte, the parallel connection's already shot out 8 bytes. Because when you're going byte to byte versus bit to byte, it's a little zippier. What else? Scanners worked on parallel for a while until SCSI became a thing. And now pretty much all of that retired and has gone to USB. Maybe FireWire. So your point-to-point link goes from the CSU-DSU of one office to a service provider network of some sort to the CSU-DSU in another office. That used to be sort of the demarcation point in a building that from here, there be dragons. Over there, it's Comcast or Charter or AT&T or whoever. The bandwidths available, and here's a fun chart to memorize. Start way down at the 56K highly compressed modem speeds. I was very excited when I got my first 56K modem. I was like, wow. It's like twice a 28.8. But then they told me that they were really full of it because what's going on is we're using compression, and if you're downloading MP3s, it doesn't matter anyway. All the way up to the OC7680, which is at 39, almost 40 gigabits per second, which is zippy. Not so bad for downloading your Homestar runners and your strong bad emails. There is a slight difference in the EU standard and the US standard, if you may recall from last week. So if you remember all that stuff we talked about way back in Cisco 1, there's this whole OSI model thing. There's also this TCP IP model. And as you go down the layers, starting at the application, that data gets encapsulated every step of the way and de-encapsulated on its way back up. So you have to do something with this stuff you're sending over the wire, and there are a couple of ways you can do it. The high-layer data link connection protocol, is Cisco's favorite and the default. Point-to-point protocol is also another option. It's asynchronous. It'll deal with IPv4 and v6, which is like all you need these days. Back in the day, you had connections like SLIP, the Serial Line Internet Protocol. That's getting way old-timey. If you can remember, like making sure you've installed WinSock so that your Windows 3.11 machine can connect to the internet. That was one of the connections you'd probably seen. X25 or LABP, Link Access Procedure Balanced, you would see actually kind of, I don't know, maybe a decade ago, more frequently Frame relay is still a thing. Some people are pushing. It came after X25. And then ATM was the thing we ditched for Metro Ethernet, if that helps at all. So like kind of put it in timeline. The cool thing about ATM was it used these cells that were always the same size. So you just started sort of spitting cells across the wire and then packing stuff inside of them. All that other stuff we're kind of going to stay away from. We will look basically at PPP and HDLC. Those circuit switch networks, those are for suckers. Plus, somebody's got to be there to set up the circuit, so it makes it hard to build a lab. So that's what Cisco's going to have you look at. So here is how the standard HDLC frame looks. You've got a flag on either end, an address, some control information, the data we actually care about, a frame, check sequence in it. Cisco uses part of that data field in order to allow multiple protocols to flow across the line. So if you wanted to, I don't know, send Apple Talk across the wire, you could do it. Anything that happens below doesn't matter. Everything that happens above doesn't matter. So maybe when you plug your Cisco HDLC gizmo into a network and connect it to a non-Cisco HDLC gizmo over a network, you might get into trouble. So sometimes they'll call Cisco's proprietary implementation CHDLC. Normally not a big problem, because when you're buying equipment for a couple of sites, you will generally want exactly the same piece of gear on both ends, unless you've got like a hub and spoke thing going on. But even then, you would probably be wary of doing multiple vendor networks over the wire. It's just a way to get a bunch of finger pointing started, so you don't want that. So if we ever set up serial interfaces, which I'm not a huge fan of, here's how you would tell it to do HDLC encapsulation. Encapsulation, HDLC. Get into configuration mode, tell it to do that. Pretty straightforward. Ta-da, you're done. And since it's the default, it's kind of what it wants to do. It only gets tricky if you want to do it another way. The trouble starts when you have to troubleshoot this line that the middle part of it belongs to some other company to maintain. So you've got a couple of options to sort of help you figure out where that problem lies. You've got the show interface serial, and it'll tell you that the link is up and that the protocol's up. It's encapsulated, so it's actually thinking about it, and then all of the minutia of what's going on in that connection. And there's a bunch of troubleshooting flowchart stuff in here. If everything's working, you don't have to do anything. But so say the serial port's down, we don't have a signal, maybe the WAN carrier is the issue, maybe the cable's faulty, maybe the hardware is broken. That's a pretty big list of things to troubleshoot. So you've got some answers there. If it's the hardware, swap out the bad parts. If the router's an issue, maybe you've got 2 serial ports, maybe you've got a spare router. So it gets pretty, your troubleshooting options are pretty limited pretty quick. You know, if you're basically saying, do we have another router we can try this with? Do we have another serial port we can try this with? If the line is up and the protocol is down, maybe we screwed something up in the configuration. If the serial port's up and the line is down, you can check your clock rate. The thing that you do for a serial interface that's different than all the other interfaces you deal with, I guess you do it with Ethernet too, is that you set the clock rate in bits per second. So the syntax is clock rate 28.8, 1200, whatever. That needs to be the same on both sides of that connection, or things aren't going to work right, or at all. And then if it's, I'll skip some of these, but if it's administratively down, you might want to set it administratively up. So it's possible to screw these things up yourself. So here, if we're looking at that, we know we're in DCE mode. Somebody actually set the clock rate. And there's a whole walkthrough on all of the different commands that you can enter in to help troubleshoot. And I invite you to pause or take a moment in your free time and go through actually typing the commands. I know everybody loves doing that. And if you have the time, take a look at the packet tracer that's associated with that stuff. So while HDLC is the default, since Cisco's kind of made it a magical Cisco protocol, if you've got to connect to some other vendor, PPP might be what you want to do. So kind of the same idea. It's an encapsulation protocol over layer 2. It does framing in a similar way. It's got this link control protocol that you use to connect to it. There's a family of protocols that you can plug into it, including the often used AppleTalk protocol, or Novell's very famous IPX-SPX protocol, and a bunch of other stuff that nobody really uses anymore. But it'd do it if you wanted to. So why would you use this? Well, there's features you might like. Not available in HDLC, but available in PPP is the ability to tell you how well that link is working. So their link quality or link quality management feature is nice. It will also do PAP and CHAP, which we'll look at in a little bit. But you may remember those terms from if you ever set up a modem. Those were the kinds of protocols you were using to establish communication. Kind of works like the OSI model. So it starts with a physical layer, has this data link layer, and a network layer on top of it. It should be very familiar with how we've done all the other protocols we've looked at in the past. The link control protocol layer provides limits on packet size. So if we've got a crappy connection and we want to make sure that there is more error checking, we can shrink those up. If we've got an easy misconfiguration, it can explain that to us. When the link needs to come down for some reason, gracefully, as opposed to just pulling the plug out of the wall, you can do that there. And if you've got a link that's flapping or is misbehaving, it'll tell you when those things are going on. The network control protocol portion of it, so we're kind of, the way we like to do this is sort of move up the connection, lets multiple types of protocols happen over the same link. So if you really did need to get AppleTalk and IPX-SPX and TCP/IP over your link, you could do that. More realistically, you might be doing IPv6 and IPv4 over that link. And it can negotiate all that stuff for you. So if you were looking at the bits and bytes of that connection, those are the hexadecimal values of the protocols in question. So AppleTalk's in there, IPX-SPX is in there, link control protocol, and PAP and CHAP, the password authentication protocol and the challenge handshake authentication protocol. Here's what that frame looks like. Starts off with a single byte that tells us, is it the beginning or is it the ending? So if you looked at it and you saw zeros bookending a bunch of ones, that would be the beginning of it. The broadcast address of 11111, because these are point-to-point connections, so we don't really need to worry about anybody else on the wire. The control sequence, so far we're up to a frame that looks like 01111, 01111, 6 ones and 2 zeros, letting us know that it's going out. Then that protocol sequence we looked at previously, except instead of expressed as hex, expressed as binary. The actual data we care about, and then the frame check sequence. So the 16 bits, 2 bytes of a calculation of the frame check. And it's just, if those don't match, well, throw it out and retransmit. So feel free to go through and fill those out. So like every good thing in networking, there's a setup and teardown. So we start by establishing a session. And as an aside here, There's a book called Autonomous about a future where biological hacking and piracy is available. And one of the things that really weirded me out about it is all the communications between the robot characters in the book start with session establishment and exchanging cryptography keys, which I thought was a nice touch. So a lot like this. So phase 1, shall we negotiate? Phase 2, perhaps we should discuss quantity and quality of transmission. And then phase 3, yes, I will let the NCPs discuss this for us. So it goes through and sets this up. It can just say skip it. We're not going to figure out what we're going to do here. We're going to leave it to the higher level protocols. Like TCP will handle figuring out window size and crap like that for it. And then once it closes down, it moves on. And it will sit there until frames come along waiting to go again. So the configure request, the configuration ACK, and we start changing network communication protocol packets. We echo those back as it starts to maintain, data keeps exchanging, maybe something doesn't work out so well and we reject it. So if that CRC doesn't match up, that FRC, the frame check, is invalid, that's when we reject the code and spit it back. And then at some point you get sick of talking to one another and you terminate the communication. So somebody says, all right, we're done here, and the link is torn down gracefully. And you do that so that your link doesn't wind up sitting around waiting to connect for the next time. So we can authenticate this sucker with PAP or CHAP. We can decide whether or not we're going to be compressing, and we can decide whether or not we're going to be using multi-link, creating multiple channels to increase bandwidth. So here is an example of a network control protocol establishment using IPCP. So we've got our link set up. We've configured our network control protocol. We've done a little data transfer back and forth. And if we needed to tear it down, we could. But IPCP can negotiate how much compression are we going to use. So are we going to try and take the data that we've got and smush it down even further, which works great, assuming that the data inside of that header is not already compressed. And then you can start adding IP addressing into it. So if there is a PPP link there that's specifically going to have routes across it that are going to need IPv6 addresses or IPv4 addresses, they get established here. Once that's all done, it opens up. We start sending traffic back and forth until we're done sending traffic, and then we say, okay, that's it. We're terminating this connection. It's been my experience that, like, on a link like this, terminating the connection gracefully happens very rarely. Like, usually, once you get one of these things stood up, the connection stays pretty active most of the time until, like, a backhoe cuts a wire, or somebody spills a Coke on the router, or some other event like that gets in our way. So we actually don't just establish connections willy-nilly anymore, although there was a time in the naive and young days of the internet where that was a thing. Oh, those were the good old days. But so somebody figured out that people being able to just connect to your modem and start typing commands on your servers was a bad deal. So we figured we would come up with some kind of authentication. So we do that. And PAP, Password Authentication Protocol, and CHAP, the Challenge Handshake Protocol we discussed earlier, are two of the early examples of how that will work. And these are the codes that wind up in the options field to tell us which one of those things we're going to do. That'll establish authentication, so you have the username and password that we're looking for, and then whether or not we're going to use compression. So there's only so much you can do about compression, but there are stacker and predictor compression protocols that you can feel free to dive into deeper. There's a magic number that helps figure out and It's just a random number that we choose to make sure we're staying in sync with one another. That if it gets screwed up, we know we've got an issue. And then we've discussed these in sort of terms of modem callbacks. This used to be a big security feature if you had a RAS server, or a remote access server. You would have this feature set up where my modem calls the home office and says, hey, I'd like to set up a connection. Click. And then the home office looks up who just called in by username and calls the phone number back associated with that username. So the idea was that you would have to not only know that person's username and password, but you'd have to hack the phone system to make that happen. Nowadays, that isn't such a big deal to hack the phone system, but that was that. So figure out how that callback is going to be determined as the last field. So after you set up your router and you're deciding, okay, the serial link is going to have PPP instead of HDLC, instead of encapsulation HDLC, you will not be surprised to learn that you tell it you're going to do encapsulation PPP. Oops. You decide whether or not you're going to use compression. So you can use the predictor or the stacker. Stacker's kind of the zip algorithm, the LZ. Decide whether or not we are going to monitor for quality. So at what point do we decide this connection is garbage and we need to throw it away and try again? And you can specify that as a percentage from 0 to 100. Again, notice we're doing these on both routers the same way. So again, you don't want those to be out of sync. So here they've set it to 80%. If quality drops below 80%, it's garbage. Bounce the line. By bounce, it doesn't do it like super fast, so it will sit. So then you can add multi-link, which allows us to have packets fragment and put back together. You create the groups thusly. So you've got a bunch of interfaces, multi-link, comprised of serial 010 and serial interface 011. You put them into a little group, do the same thing on the other side, and now these two serial ports bind together to become a multi-link bundle with a specific number. And then tearing it back down is the typical Cisco setup, no command. So go back into the interface, no PPP multi-link, go back into the interface, no PPP multi-link. Sort of like, yeah, sort of like Ether channel. I was going to say bonding, but that is the word for it. So then you get all that set up. Well, now you got to verify that it's working. Show interface serial again. We'll tell you what kind of encapsulation we've got. That's the only one we do a demo of. Show interface serial. We'll display information about the serial interface, and then show PPP multi-link. If that's what you've got up, we'll tell you that, here's multi-link 1, the remote endpoint here, the local endpoint here, which connections on that are members of that multi-link. So serial 1 and serial 0 are both members, and they've been active for X amount of time. And those are your friends when troubleshooting these in real life and when troubleshooting them on packet tracers. So PAP, two-way handshake. The remote router sends over username and password, which we might remember, not always a great idea to send over something without any encryption. CHAP got all super high tech, and they added a hashing function to the password so that you don't send a password over a wire, which is like a good idea. And then if the hashed value corresponds to the hashed value on this end, it lets you in. The reason we do that should be all too obvious at this point. So that's bad. You don't necessarily want that. This is better. So we start that three-way handshake. We send over a hashed version of it, and based on whether that hashed version matches what we've got in our little brain, we're good to go. Even though it's only MD5, which is kind of old-timey, which you could probably crack given enough time, it sure is better than just sending a password across a wire, which we don't like to do. So how do you set that up? Here's the PPP authentication command. Tell it, will we be doing CHAP, PAP? Will we be doing both? And will we do PAP, CHAP, and perform PAP authorization before CHAP authorization, which is probably not what you want to do. So if you've got CHAP set up, you probably want to try that first, hope it works, and if it doesn't, and it falls back to PAP for whatever reason, fine. When you set that up, give it a username with a password secure command, and do the same thing on both sides. So PPP authentication PAP, PPP PAP, sent username is R1, password is your password, and you're done. On router 2, go back in, do much the same thing, set the authentication, set the username and password, and you're off and running. Darn near identical. And then there is a packet tracer I invite you to enjoy. Who doesn't enjoy a good packet tracer, eh? Where you can walk through all those processes. Or a lab. So now you've got all that set up, and it breaks, and you're trying to figure out why. So we must troubleshoot. If you want to see what's going on in that, we've got debug options. You can debug the packets. You can debug the negotiation process. You can look for errors associated with that connection. This would be a good way to point the finger at your ISP. Hey, man, we're getting all sorts of errors in here. We can see if the authentication is screwed up, if the compression we've enabled is broke, or if we're getting some problems with the callback control. The callback control protocol, or the CBCP, also uses the Microsoft callback protocol. So it will tell you if those things are screwed up. And if we're getting like bad packet sequence numbers, all sorts of useful stuff. So here's the kind of things you will see when you are debugging the packets. Last in and out, when they happen. When you debug the negotiation, you'll watch the link come up, down in this case. They restarted it so that they can capture it. You'll see it send the notification, process the message, figure out what's going on. Here we're establishing the connection, and so on and so forth till we get down to authenticating. Here we do our CHAP challenge. We get all connected and we're off and running. And then here are the error messages we might see. We're getting a bunch of receive failures. Oh, and it turns out that this one has been looped back, so that's not good. So it's a wire connected to itself. You don't want that. PPP authentication will show you what's going on when you're trying to log in. So in this case, we can't authenticate because we didn't get a username from the person trying to connect. That's going to be a problem. So somebody needs to go back onto that router and set up the username. And if that was something we were trying to do over the network, we're about to discover why it's a good idea to have a phone line plugged into the back of your modems. Or to have a modem plugged into the back of your router, more accurately. And so this is the packet tracer that's assigned and will be graded. 2512, the Skills Integration Challenge. And that is point-to-point communication protocols right there.